So far so good? Pretty straightforward? Okay, so then each of your critical points, you want to run them through this ringer. Okay. If I'm at the critical point 3, 3, D equals, as a matter of fact, I'm not sure why I did this. I tend to leave D in this calculation because where's my second partial with X in this? Right there. Well, or just make note of it. No matter what my D value is, my second partial with X is positive. So, I mean, you really have nothing to plug into to check that. Your second partial with X is always going to be positive. So, when I check D, D's value really only depends on Y. So, okay, it's kind of convenient. If I plug this value of Y in, 12 minus 4 happens to give you 8. But it's not the number that you get back, it's the sign of the number. So, what I tend to do is if I plug this in, I just say I get a positive result because I'm really just looking to check the sign of D. And fxx is always positive because it's the constant positive 2. So what is that implication? The critical point 3, 3 produces what for the surface?
Local max.
Yeah, you're at the bottom of concave up. So that means this critical point is at the bottom of a bowl as in a valley. So it should be a local minimum. Yeah. So if you have all this as your work, you could really just circle that whole line because this is the conclusion I'll really be looking for, is you have a local minimum at the critical point 3 for X, 3 for Y. Okay. One more to check. At the critical point -1, -1, my D value there is going to be, now be careful, you're plugging -1 in for Y, so that's technically -8. And you need to check the second partial with X. I mean, it's always positive too, but whenever D goes negative, what's your conclusion? Let me remind you. If D is positive, that's the only time you could get a min or a max. In the instance that D is negative, your only conclusion is saddle point. So no need to cross-reference it with anything else. If you get a negative D value, then that implies you have a saddle point at that critical point. And that's the rudiments of how you work a D-test problem. From pillar to post, from beginning to end, it's about finding the critical points here that we did on that second page, and then taking each critical point in tandem and using the D-test on it to see what your conclusion is. So you don't always have a picture. I mean, there are lots of handy apps out there that you can get for tablets. How many of you have a MacBook of any variety, of any generation from the last like 8 years? There is a preloaded software called Grapher. If you go to the Finder, then go to, I think it's maybe applications or maybe utilities. Eventually you'll see a little program called Grapher. Its syntax is kind of tough. You can type in some basic function equations and it'll graph 2D, 3D, polar, vector fields, it'll graph level curves and stuff. It's a really handy graphing tool. But it's built into the Mac, so it's kind of nice. If you have any kind of tablet, just go to the app store or whatever for your tablet and then type in 3D Grapher if you want to be able to sort of see some of these functions, and it'll take that syntax, usually type it in and produce an image. My printer was kind of weak this day, but when I printed this off, but here's a picture of this function, or what this function roughly looks like. And it's technically that same software package I pulled up in class last week. So the local minimum that we found from the critical point 3, 3, let's see. This is the positive x-axis right here. Here's the positive y-axis. No, that's a lie. I had that reversed. This is positive x, that's positive y. And so the 3, 3 point in the domain, when you plug it into that function, it gives you this coordinate in space, this z coordinate in space from plugging in x equals 3 and y equals 3. And if you look at it, it looks like it's at the bottom of a bowl, okay? To see the saddle point, I had to rotate the surface around to the other coordinate, -1, 1. So again, it's right in there. Saddle points kind of, they look just like saddles, but on some surfaces they get so steep it's kind of hard to see the saddle-y behavior. So sometimes I may sort of scrunch the surface down and scale it down a little bit, dampen it, so you can sort of see that in one direction you have concave up, but in the other direction you have concave down, which looks like the middle of a saddle or the middle of a Pringle potato chip. I should have brought Pringles tonight. That'd have been a great idea, okay? The only other food that we talk about in this class, well, no, it's really just Pringles. Because you first see Pringles in this class when you talk about the hyperbolic paraboloids, all the oids back in the first chapter. So that's when you first meet the Pringle in Calc 3.
Can you do bugles for like conic sections?
Bugles, you can talk about cones, yeah. We can do bugles for cones, and
Cocoa Puffs.
I guess, for cylinders we could do like a Twix and sort of, make it a little bit rounder, maybe. Or no, one of those little push pop things.
Yeah.
Those are cylindrical. Those are awesome. Okay. Any questions despite my silliness?
We go to the cafe.
If I'm making you hungry, feel free to go grab me something to eat real quick if you need to. All right. So let me show you another example because it's good to see some practice with this. Simply because, in all honesty, folks, the toughest part of a D-test problem is usually this, finding the critical points, because it brings back to bear some old algebra that you haven't really done in a while, And this system of equations right here, the equations 1 and 2, that's the whole crux of finding your critical points. Sometimes that's nice and linear, which means you can use any means of solving a linear system. But 9 times out of 10, it's a nonlinear system where you have to do some kind of substitution or elimination like this. Chris.
It was a saddle point because the d was negative, but the fxx was positive.
Well, now you got to be careful. If I evaluate fxx for this particular for this whole function is always positive 2, which means any slice you do on this surface that's parallel to the x direction should always be concave up. And concave up doesn't always mean this, doesn't always mean U-shaped. Sometimes concave up is, well, for example, the exponential function. The exponential function does not look like a U, but on its entire domain, it's concave up, okay? And concavity can just be really very subtle. But in the x direction, this thing is always concave up. In the y direction, if you check fyy, fyy was actually in our d value, right here. If I take this and plug it into just fyy, notice you get negative 2. So just checking the x direction versus the y direction, this surface is concave up, maybe kind of like that in the x direction, and then it's concave down in the y direction at that point in the middle. So because you have that crisscrossed concavity, that's why it qualifies as a saddle point. But you got to be careful. It's not always in just the x or the y direction. Sometimes the crisscrossed concavity, that's almost a tongue twister, can be kind of off kilter a little bit. Maybe it's 30 degrees off the x direction and 22 degrees off the y direction, and your crisscrossed concavities like that, So it may not always be just dependent on fxx or fyy. I feel like I'm doing Ultraman or something like that. I don't know what Japanese TV show. But no, it doesn't have to be in just those two directions. It could be in any direction where you have mismatched concavities. That's why D is sort of an omnidirectional concavity checker. If D is positive, you're guaranteed to have nice concavity behavior. Okay, but if D is negative, you've got loopy concavity behavior. You have a mismatched concavity. So that's why that's the only criteria for checking a saddle point is if D is negative, boom, you're done. Saddle point. Okay. Any other questions?
Dude, your shirt's awesome. You're welcome.
So let me show you another example. And I'm going to go to the whole page for this one. So so we'll do the critical points at the top and apply the d-test at the bottom. Okay? And they all set up the same way. Get our critical points. Get our CPs. So you want to set your first partial with x and your first partial with y at the same time equal to 0. So for this one, first partial with x is going to be 6x squared plus y squared plus 10x, and then you're done. So force that to equal 0 because you're looking for where you have 0 slope in just the x direction, and you want the j component of your gradient to go to 0 also. So you set the first partial with y, which would be 2xy plus 0 plus 2y equal to 0. Okay, now I'll go back and renumber these, equation 1 and equation 2. Okay, terribly not linear. squares here, and a product of x and y there. All three of those break this from being a linear system of equations. So you want to come up with some kind of way of making a systematic set of substitutions. Some kind of, look at the two equations and which of these two equations would lead to something that's easy to plug into the other equation. First off, I'm asking you just hypothetical questions. I know what to do here, but what are you sort of pondering as your options on how to start solving this system? Which of these two equations looks like it might be easier to start working with?
The y, but that's
Even though x and y are both present, you're right. Does everybody see why this might be a little more simpler to work with? I mean, what makes you look at this and see that there's some more potential, or maybe it's easier to work with?
There's
No exponents.
They're all linear.
They're all linear. It's factorable. And I can't really factor anything here because I have the unlike terms x squared and y squared, and maybe that's what I want to substitute in too. So in this case, you probably want to take the first partial with y and figure out some kind of substitution based on it. Any kind of truths you can get from that second equation. So let's consider maybe factoring it. Now what you don't want to do is you don't want to divide both sides. Anybody tempted to divide both sides here by y? If you divide by a variable, you're going to lose some potential solutions. So don't divide by a variable, okay, in terms of trying to eliminate it. You want to keep all the variables in the mix because you want to try to see what implications I can get from that equation, what truths can I get from that equation. So it's set equal to 0, and I can take out a GCF of 2y. So, since it is factorable, there are two truths, plural, that I can get from this. What is one thing you know has to be certain from this statement in terms of possible solutions? X should equal -1, okay? And then I can actually take that, and keep in mind, we haven't used the first equation yet. I'll need to take that x equals -1, which is true for this equation. That does solve this equation, or it satisfies it. And then plug it into this one for x, and then see what y values that leads to. So that's like one case that I can get from this. What's another case I can get from this? Y equals 0. Since it is factored and set to 0, there are two truths. Sounds like a philosophy class. So I'll call them cases as opposed to truths. All right, two things we know to be certain from this second equation is I know y equals 0 annihilates everything and makes it equal to 0, so y equals 0 satisfies this. See what it can generate from the first equation. And then in a separate case, in a separate scenario, a separate substitution, take this, plug it into the first equation and see what else it leads to. So you got two different things to do here to find out what values this y equals 0 and this x equals -1 should pair with. Does everybody understand why this doesn't guarantee -1, 0 is a critical point? Can you see why simply solving this from the second equation only tells me that that's not guaranteed to be a critical point as a coordinate pair? Why?
Because you haven't tested the first equation.
You haven't done anything with the first equation. You've got to come up with the coordinate pairs that satisfy both equations at the same time. So be careful not to mislead yourself into thinking this is a viable critical point, because you haven't checked it in the first equation yet. So that's why you want to take each of these one at a time. So in two separate steps, we're going to take our cases and plug them into equation 1. So if I take the y equals 0, plug it into a fresh copy of equation 1, I get this statement. 6x squared plus nothing plus 10x equals 0. So what that means is any solutions I get from this equation are going to pair only with the y value 0, because we're getting this new fact based on that substitution. So whatever critical points this leads to, we'll have a y coordinate of 0, guaranteed, because that's the substitution that led to this. So this is quadratic, and it's only in terms of x, so it should be straightforward to solve. Actually, I'd do factoring here too. You can take out a 2x. You're left with 3x plus 5. So based on the substitution y equals 0, we get how many solutions for x?
2.
You get 2. You get x equals 0 also. And from this other factor, you get x equals -5/3. okay? So everything we got here is all based on using the fact that y equals 0, that original substitution. So that means the critical points this generates are x equals 0 paired with y equals 0, and x equals -5/3 also paired with y equals 0. So just that one substitution led to two different critical points we need to check in the final d-test. Okay? What do you get when you plug x equals -1 into the first equation?
Square root of -16. Or is that incorrect?
Be careful.
No, it's positive,
Yeah,
excuse me.
plus
So
minus
it's plus -2. Yeah, because it's square root of positive.
You should get plus or minus 2 eventually. Yeah. So if you take x equals -1 into a fresh copy of equation 1, and this will be easier to solve. Both of these x's replaced with -1, so that's still going to be +6 from -1 being squared. So there's no sign change there. And then plus your y squared term, but then 10x becomes -10 because of the negative number you're plugging in. So to solve this for y, it's just a matter of eventually taking some square roots. Bring all the constant terms to the right. That leads to a y squared equals +4. And you got to be careful. Square roots, don't forget that plus or minus you got to put there. So we get two new critical points because these values are based on what? All based on x equals -1. So we knew the first half of any critical points we were going to get here already. We knew that the x coordinate is going to have to be -1. We get two values of y that pair with them. So the CP's here are -1, 2 and -1, -2. So all in all, this surface produces 4 different critical points to check in the d-test. Okay? Any questions so far? How many of you have done algebra kind of like this before? A handful of you. It's a tragic thing about our pre-calculus class. We really need to add the topic of nonlinear systems of equations because some of you only have experience solving linear systems. You know, here's an equation of a line, here's an equation of a line where they intersect, one-point solution. And some of you have never seen nonlinear systems of equations. I mean, technically, if you look at the graph of this, you're finding the intersection of an ellipse with whatever the heck that graph is. Okay, probably some kind of rational function. And apparently, when their graphs overlap, there are 4 coordinates of intersection. Okay, so if you had a graphing software that allows you to graph things like this, you could probably do the intersect function on your calculator to find these points. But in most cases, the algebra is what you have to fall back on to find out those points of intersection. So that's usually the toughest part, simply because of I guess some students have an algebraic deficit coming in here and not experiencing those nonlinear systems. So once you get the critical points, in all honesty, the hard work's done. Now we want to use the d-test. So let me construct d for this function. D is, let me remind you, fxx, f second x partial, times fyy, f's second y partial, minus fxy squared, the mixed second partial squared. So in this case, fxx is going to be, in this case, you've got to be careful, it's a binomial. Second partial with x is actually 12x plus 10 times fyy, which is 2x plus 2, and then the mixed second partial, taking this partial with respect to y now, would give you just a 2y. So in most cases, let me make sure that looks like a 2, it looks like a question mark actually. In most cases, I just leave d in this raw form because you remember that's the position of fxx, so we can check its sign at the same time of checking d when we're done plugging in our critical points one at a time. So now we're committing to plugging in 4 different critical points. Okay, so checking our CPs. Let's do the easiest one first. The origin is probably going to be the easiest one. At 0, 0, if I plug in 0 for all these x's and y's, this becomes, and let me just jot it down, d is going to equal positive 10 times positive 2, so 20, minus 0 squared. So d is a positive number, and do you see the convenience of writing it out like this? in this sort of raw calculation form. At the same time, you can double check and cross-reference fxx. Fxx is positive, fyy incidentally also happens to be positive. So in both directions, you're concave up. So this critical point is at the bottom of concave up, positive d, positive second x partial. So that means you have a local min there. Can you guys read my handwriting? You've spent 3 days with it, so hopefully it's pretty legible. It's kind of terrible back in January, but it gets better as the semester goes through, so you get me kind of midway through. New critical point to check. Let's do the funky one with the fraction method. At the negative 5/3 for x, 0 for y, we carefully calculate d here. 12 times this x is going to be 3 to 12, 4, negative 20 plus 10. So you actually have a negative 10 there when you plug negative 5/3 into 12x plus 10. 2x plus 2 is going to be negative 10/3 plus 6/3, so negative 4/3, minus, this only depends on y, so you're subtracting goose egg, and it's positive. Don't really care about the numerical value, but since this is subtracting 0 and you're doing negative times negative, you're getting a positive d value, so you possibly have a max or a min. Cross-reference it with that number. That fxx being negative means you're at the top of concave down in terms of the x concavity. So top of concave down is a maximum. Same conclusions as the first or the second derivative test from Calc 1. When your second partial is negative, you're at a max. When your second partial is positive, you're at a min. So it's just the next extension of that. The only new thing here is to double check the d value too. So fxx is negative, so that means top of concave down, you have a local max there at the negative 5/3, 0 coordinate. Any questions so far? Any what ifs or what the heck or? Okay. The sponges are absorbing tonight, so I guess y'all are kind of getting this pretty well. 2 more critical points to check. These over here that sort of alternate the y-coordinate signs, which leads me to believe the only part of D that's going to be influenced by this is which one? The only change in these two is the y-coordinate goes from positive to negative 2.
Yeah.
So, will you actually get a different D value for both of them?
Yeah, I got D is negative and it's a saddle point for both.
Yeah, because the only use of y in your D is right here, and it gets squared. So since you're changing from positive 2 to negative 2, that's going to be the same quantity. This is going to be the same quantity. So we may be able to get away with just checking one of these. So at the coordinate negative 1, 2, negative 1 for x means this is going to be negative 2 times 0. I like that. Minus 2 times y, so 4 squared. So since that wipes out the first half of D, and that negative doesn't get changed from squaring this, that means you get a negative value of D at that critical point. No need to check your second x partial, because you just found the saddle point. Okay, and I believe the same thing happens to the other coordinate. Because the only thing you're doing is you're changing the y-coordinate from positive 2 here to negative 2 in the next one. So that means you're still going to get the negative 2 times 0, but in this case it's minus negative 4 squared, technically. But the squaring there does wipe this to 16, but you're still subtracting it. So no change in the sign of D, going from the third to the fourth group. And the saddle point. And those are the conclusions I'm looking for. It's just, of the critical points you got, what are their role on the surface of this function? Now, what I've done on the test before is, like, if I know it's a problem where you get 4 or 3 critical points, I'll probably say pick any two of your critical points and apply the d-test it. So that way, I'll know which one you're choosing, you let me know which critical points you're testing, show the use of the d-test, and show your conclusion. So you may not have to check all of them if you get you know, a plurality of critical points like that. But in the homework, go in and get practice of doing it, okay? I think that maybe the worst case scenario is 4 critical points have to check. Okay? Now, let's apply this to something, okay? In Calculus 1, after doing the first and second derivative test, you visited a set of problems, well, I mentioned it to some of you earlier, like where you have a fixed amount of material, like say 20 square yards or 20 square feet of a rectangular box, and you want to fold up the sides and make a little rectangular piece of cardboard. Then you want to fold up the sides and make a box out of it. And of all the different ways you can allocate the dimensions of that box, which one's the maximum? So you did these optimization problems in Calculus 1, where you're trying to find the maximum volume, the minimum surface area, the shortest distance, things like that. You're revisiting problems like that, but in some cases, doing them in higher dimensions makes the problems a little bit easier. So let me show you an example of one of them. This next example right here. Optimization revisited from Calculus 1. Bless you. Did you bless a hiccup? What the heck? Let's bless a hiccup. Okay. What is the shortest distance from the point 1, -2, -3, some point out there in space, a fixed point there? What is the shortest distance from that point to this plane? First thing you probably want to check is to make sure that point isn't on the plane, because otherwise this is a darn easy problem. The point's already on the plane, okay, 0. It's on the plane, there is no distance, so boom, solved. Next problem. If you plug in 1 for x, -2 for y, and 3 for z, that's going to be 3 minus 4 is -1, plus 3 is 2. So it doesn't equal 12. So sure enough, this point is not on the equation of this plane. Now here's a picture of what you're trying to figure out. If you want to pair this with a picture. Let me just use the marker over here. Okay. So this plane's out there in space, and the handy thing about this equation of the plane is when it's written in this form, you can find the x, the y, oh sugar, crap, the y and the z-intercepts by doing those 3 values set equal to 0, a pair at a time. So like to find your x-intercept, if you let y and z both go to 0, that means you're going to find a point on the x-axis. And what would the x-intercept be if 3x is equal to 12? 4. X-intercept is 4. So this plane would look roughly like this. X-intercept at 4. So there's the point where the plane is the x-axis. Where would the plane hit the y-axis? Set x and z equal to 0. 4y equals 12 gives you a y value of 3. So right there is the y-intercept. The z-intercept, x and y go to 0, so you're left with z equals 12. So it's a kind of steep looking plane. Okay, so somewhere about right there. So the plane, just the first octant view of this plane looks something like this. It kind of makes this little tetrahedron in the first octant, roughly. Very roughly. Now this point is not in the first octant. This point is located +1 for x, -2 for y, so I've got to go back this way. So -2, about right there. And then +3 for z. 1, 2, 3. So let's say for convenience the point's right about there, somewhere behind that plane in that octant adjacent to the first octant. So of all the distances, I want to figure out what's the shortest distance from that point to that plane, you see? Now, there's probably a geometric way to do this without using calculus. No, in 3 dimensions, I don't think it's going to be that easy. In most Calculus 1 problems where you're trying to find, the way this showed up in Calculus 1 is you probably had a parabola like this and a point right here, and you want to find out what's the shortest distance from that point to the parabola. If you could turn it into a 1-variable scenario, you could probably use geometry. It's hard to do that here because of the higher dimensions. So what we want to figure out is, first off, what's the function we want to maximize or minimize? What attribute do we want to maximize or minimize here? Distance. So, shortest distance, that superlative right there, shortest, indicates is an extreme value, the minimum distance. So, You want to minimize or find a minimum distance in 3 dimensions. Okay, so what do you know about calculating the distance in 3 dimensions? Were you introduced to the 3-dimensional distance formula earlier in the semester? Maybe? Well, it's sort of like the magnitude of a vector. If you think about the magnitude of a vector, you have to do I component squared plus j component squared plus k component squared. If you represent a vector as difference in x's, difference in y's, and difference in z's, or the 3 components, the distance formula in 3D looks like this. It's pretty much analogous to the 2D distance formula. See, that much right there is your 2-dimensional distance formula with the radical all the way over it. The only difference is we're also dealing with a z-coordinate. So technically, if you think of x1, y1, and z1 representing the tail coordinate of a vector, and x2, y2, z2 representing the head coordinate of a vector, each of these are the head minus tail calculations that give you the components of that vector. And then this is just the magnitude of the distance along the vector between those 2 points, from tail to head. Okay, so that's kind of where the 3D version of the distance formula comes from. I want to minimize this, but I'd like to turn this into a function of how many variables. Ideally, doing the d-test, how many variables do we have on the parent function in each example? 2. A function of x and a function of y. So I probably want to keep x and y in the mix, but I may want to come up with some way of eliminating the use of z.
Using the same point on the plane and on the point.
And that's the thing. One of these points we know. One of the points in this distance formula has to be our fixed point. Okay? So, for, I guess, no real reason, for convenience, I'll let this represent the x1, the y1, and the z1 that I plug in after the minus in each of these quantities. Okay? So let me edit that. There is a method to this madness, I promise. Okay. Leave yourself about a couple of fingers worth of distance here, because there's something we're going to put here. Okay. Originally, oh, good thing you're doing this in pencil.
Yeah.
I just didn't want to commit to a whole new line of pen text on my notes that I'm writing here. So I'm committing to using x1, y1, and z1 as the fixed point that we're located at in space, the one we're trying to minimize the distance. What's the other point going to come from? We're calculating the distance to what?
So are we going to solve for z?
Some point on the surface. Okay? So we want to, keep in mind this equation has x's, y's, and z's in it. So if I let the dummy variable x here represent an x coordinate from that plane, the y coordinate here represent a dummy variable from the y coordinate on that plane, what can the z coordinate be replaced with? What does it have to be replaced with?
12.
Pardon?
12.
Not 12.
12 minus 3x.
12 minus 3.
Yes, you have to keep in mind this equation represents all the points on the plane. So we're committing x and y as being dummy variable representations of points on that plane. But the only thing that tells you the z-coordinate is if I know x's value is x and y's value is y, the z-coordinate has to be 12 minus 3x minus 4y. So you actually have to tie in the plane's equation into this mix in some way, shape, or form. So, let me make sure you're aware of this. In this equation here, x and y represent a point on the plane. So therefore, that forces any other use of x and y to be the same x and y in that